In this chapter, we're going to go over things like how to write a Dockerfile and how to use it. But let's start with a basic question. What is a Dockerfile? Basically, you can think of a Dockerfile as a script or a recipe which you can feed to the Docker build command to create new images. Dockerfiles are surprisingly useful. To see why, consider a scenario where you have to create an updated version of an existing image. Furthermore, let's say that it took hundreds of actions to build the original image. Building the updated image by hand using the commit command would be laborious and mistake-prone. But if you had a Dockerfile, the process would be faster and more reliable.
A Dockerfile is made up of comments, instructions, and parser directives. Note that instructions are not case sensitive. However, the convention is for instructions to be uppercased to distinguish them from instruction arguments. Here's an example of a real Dockerfile. It just happens to be the one I used to create the true Kubernetes/clock image. Don't worry about the details yet. This is just to give you a feel for what Dockerfiles look like. The build command is used to create a Docker image from a Dockerfile. Here's how it works. The build command takes a Dockerfile and a context and then builds a brand new image for you. The context is the set of files from the path or URL that you will supply as an argument to the build command. If the purpose of a Dockerfile is to act as the recipe for building new images, what's the purpose of the build context? Well, the Dockerfile may have one or more instructions that copy files from the build computer into the resulting image. For example, the Dockerfile may copy an executable file and its config files over to the new image's file system. The source of those files is the build context. Here's why. The Docker daemon is responsible for actually building the image. Since the daemon could be on a completely different computer than the client, we need to pass the daemon all the files that it will need to build the image. Those files are the build context. To be a little bit more specific, the files and folders at the context path are recursively copied over to the daemon. Thus, you want to make sure that the build context is as small as possible. Therefore, don't include unnecessary files and folders in the context. Copying them will just slow things down. That's why it's a good idea to put your Dockerfile and whichever file it needs in an empty directory, then build from there. Okay, why don't we take a look at an example? We are going to build the clock image from the Dockerfile we just looked at. Notice that the current working directory just has a Dockerfile and a Python script called clock.py. By default, the Docker client looks for a file named Dockerfile, capital D, lowercase Dockerfile, in the build context directory. In this example, the current directory should be used as the build context. Therefore, here's how you build the image. Each step in the build process corresponds to a Dockerfile instruction. Let's review. The image that we just created doesn't have a repository name or a tag. Thus, the only way to use it is by referring to the image ID. This is annoying and kind of confusing. What I'm trying to impress on you is that you should always give your image a name and a tag too, probably. This makes them much easier to work with for us humans. Here's an example of how to give the image the name clock with the tag v1, both arbitrarily chosen by me. Ta-da! Note that we can name a Dockerfile something other than Dockerfile. Likewise, we can put it somewhere other than the root of the build context directory. But then you'd need to tell the client where the Dockerfile is using the -f flag. This is more work and less intuitive than using the standard Dockerfile name. So don't get creative unless you need to. Why don't we go over the Docker build process, i.e. what happens under the hood when you run the Docker build command. The first thing that happens is that the context is copied from the Docker client to the Docker daemon. The reason this happens is because the daemon and client might be on completely different systems. Keep in mind that the copy operation is recursive. This means that for this example command, all files in directory and all of its subdirectories are copied. Likewise, if this is the command, then the repo and all of its modules are copied to the daemon. The next thing that Docker does is perform some basic validation of the Docker file. If it finds a problem, then it aborts the build process. Next, the Docker daemon executes the Dockerfile instructions sequentially. The new image is created, and Docker outputs the image's ID to the terminal. Finally, Docker cleans up. In the previous section, we learned that the whole build context is copied over to the Docker daemon. To reduce build time, we want to do everything we can to reduce the number of files that are copied. To this end, you can create a dockerignore file to exclude files in the build context from being copied over to the Docker daemon. Here's how it works. The first thing that happens when you build an image is that the Docker engine looks for a file named .dockerignore. This is a special text file which contains a list of new line separated file patterns. These patterns tell Docker which files to ignore and not copy over to the daemon or include in the final image. Take a look at this small example dockerignore file. The first line is a comment. The second line excludes files in the root context directory that have an MD extension. The third line excludes all files called temp, which are subdirectories of the root context. The question mark matches any one character. Thus, the pattern excludes things like fool and food. The double star pattern matches 0 or more directories. Thus, the fifth line excludes any file with a .log extension anywhere in the context. Lines starting with an exclamation point are exception patterns. This pattern tells Docker not to exclude readme.md files. When it comes to exclusion patterns versus exception patterns, the rule is that the last matching pattern wins. Let's look at a couple of examples. This excludes all MD files except readme.md. This is because the exception pattern came after the exclusion pattern. In this case, the first line says, make an exception for the readme.md file in the root context. However, the next line excludes all MD files in the root. This also excludes readme.md. Since the exclusion pattern comes later, it wins. That's it. The from instruction specifies the starting image from which Docker should build a new image. Subsequent commands add additional layers onto the new image. The from instruction takes the name of the parent image. You can optionally include an image tag. When you don't specify a tag, it's equivalent to including the latest tag. It's best to avoid using an image with the latest tag. You see, the quote-unquote latest image can change over time as new versions of the image are built. After the image name and tag, you can optionally include an as name clause, but it only comes up in multi-stage builds, which we'll go over later. Any image can act as a parent image. Usually, you'll use a stripped-down OS like Alpine or BusyBox. Then, you'll add the utilities and programs that you need. This keeps your Docker images small and fast to download. Rarely, you may want to create a base image. This is an image which has no parent. You can create a base image either by not including a from instruction or by using the from scratch instruction. Note that scratch is not an actual image. It's just a reserved word that tells Docker to start out with no parent image. The run instruction does the following things. Starting with the current image, which is the parent image plus all of the layers that have been added so far, the run instruction creates a new layer on top of the existing image. Then it executes the command supplied as an argument to the run instruction. Finally, it commits the resulting changes to the new layer. The image that you're building now has this new layer baked on top of it. There are two ways of writing the run instruction. The first one is called shell form, because commands in this format are executed in the default shell. This can be useful when you need capabilities like environment variable expansion, which is something that's done by the shell. For example, You can also write the run instruction in what's called exec form. The exec form takes a JSON array as an argument. The first array element is the executable, and the subsequent array elements are arguments for that executable. Note that each array element must be surrounded by double quotes, not single quotes. So far, the differences between the two forms are mostly cosmetic. The big differentiator is the fact that the shell form runs commands in a shell, whereas the exec form does not. Thus, this first instruction is equivalent to this second instruction. The copy instruction creates a new image layer and then copies the specified files from the build context into the new layer. Just like the run instruction, copy has two forms. Thus, this copy instruction is equivalent to this one. On the other hand, this copy instruction is not equivalent to this one. In the first instruction, both the and file are treated as sources to be copied over to temp. This is because the copy instruction can copy multiple files at once. In the second instruction, the source is the file, a single file with a space in its name. The source path of a copy instruction must be specified relative to the build context's root folder. Recall that the build context is just a copy of some files from the machine where your Docker client is. Therefore, the path of every copy instruction must be inside of the build context. Basically, you can't do something like this because ... /source is outside of the context. You may use an absolute path or a relative path when specifying the destination of the copy instruction. For example, the first copy instruction copies the file to the directory absolute path on the new image. The second copy instruction uses a relative destination path. The destination is relative to the path specified by the WORKDIR instruction, which we'll get to in a bit. When no WORKDIR instruction is specified, paths are relative to the image's root directory. When part or all of a copy destination path doesn't exist, Docker will create it for you. Docker will automatically create the directories missing1 and missing2 for you. If the copy source is a directory, then the entire contents of the directory and its metadata will be copied over to the new image layer. But the directory itself isn't copied. Therefore, the destination must be a directory and end in a /. What do you think the difference is between these two lines? The first line copies some file over to the root directory of the new image. But note that the file is given the name destination_x, not some file. The second line copies some file to destination_y/some file on the new image. The add instruction is basically just the copy instruction on steroids. You see, the add instruction does everything that the copy instruction does, plus two additional things: copy from URLs and unpack tar files. First of all, the add instruction allows you to copy files from a URL. For example, this downloads a file from example.com/tiny and copies it to dest. In the second example, a file is downloaded to dest/tiny because the destination is a directory and not a file name. Docker derives the file name from the URL. That's why the file gets saved to here. Keep in mind that you can't use the add instruction to copy over files from a URL which requires authentication. In those cases, you need to use the run command with a utility like wget or curl. The second thing that the add instruction can do, that the copy instruction cannot, is automatically unpack tar files. However, the outcome depends on whether the source refers to a local tar file or a remote tar file. If the tar file is local and the file has been compressed using a compression format that Docker recognizes, then the add instruction will automatically uncompress and extract the file before copying it over to the destination. Resources from remote URLs are not decompressed. Sometimes you need to set the current working directory. The WORKDIR instruction sets the working directory for the following instructions: run, command, entry point, copy, add, and WORKDIR. It's analogous to cding to a directory in Linux before executing some additional commands. Here's an example. The result is x/y. The purpose of the entry point instruction is to define an image's default application. When you start a container, the first executable that it runs is the one defined by the entry point instruction. Don't confuse this with the run instruction. Remember that the run instruction executes during the image build step. Run creates a new image layer and then executes the command passed to it. On the other hand, the entry point instruction executes when a container starts up. Entry point is how you set the primary containerized application, i.e., the first thing that runs in the container. The entry point instruction has two forms. Just like the run instruction, the first one is called shell form and the second one is called exec form. The former runs the command in a shell, whereas the latter does not. Thus, these two lines are equivalent. There's a very important difference between the two entry point formats. In fact, it's the cause of a very common tripping point for new Docker developers. Let me demonstrate. Here's a simple Docker file, albeit one with a non-standard name. It creates images for a small Python program which outputs the numbers in the factorial sequence. Let's use the Docker file to create an image called factorial. Since the Docker file has a non-standard name, we need to use the -f flag to specify it. Next, we're going to run the factorial image. In a new terminal window, let's try and stop the fact container. While doing so, we're going to time how long this operation takes. As you can see, it took a little over 10 seconds to stop. That's way too long. The container should have stopped almost instantaneously. Now recall that the stop command sends the term signal to the container to stop it. After a grace period of 10 seconds, Docker sends the kill signal to force terminate the container. Coincidence? I think not. Let's investigate. Take a look at this shell script called signaltrap.sh. All it does is trap operating system signals and prints them out. We are going to use it to figure out what's going on. Here's how it works. The trap command runs in the background waiting to trap the target signal and then run the trap event code. For example, this little script is designed to catch and trap the interrupt, quit, and term signals. When it does catch one of these signals, it executes the corresponding echo code to notify us. We're going to start by using the shell form Dockerfile to create an image which theoretically traps the term signal sent by the docker stop command. Since the Dockerfile has a non-standard name, we need to use the -f flag to specify it. Once the image is built, let's run it using the name Shelby. Now let's open a new terminal and try and stop the container. So the script never caught the term signal. That's strange, right? There's actually a good reason why we see this behavior. Here's what's going on. When a Linux signal is sent to a container, it's only passed on to the program running as PID1. The signal is not broadcast to all processes in the container. In this example, the shell is PID1 because we use the shell form of the entry point instruction. Now the shell does not forward signals to its child processes. Thus, the signaltrap.sh script never receives the term signal. In summary, your process won't terminate because it never receives any Linux signals. But the shell won't terminate until all child processes have terminated. Finally, the container won't terminate until the shell terminates. This is why Docker stop has to send the kill signal to put the container out of its misery. Thankfully, there are a few solutions. The go-to solution is to use the exec form of the entry point instruction because it does not run a shell. Instead, it runs your command as PID1. This means that your application will receive Linux signals. For example, here's a variant of the previous Dockerfile, but entry point is in exec form. Let's create the image. Then let's create the container. Now let's open up a new terminal and try and stop the container. Notice that the container did trap the terminate signal. However, it still takes 10 seconds to stop, which means that Docker still had to forcibly kill the container. You see, by trapping the terminate signal, it's now up to the script to decide what to do with that signal. This script just prints out the signal and doesn't call any exit code. My rule of thumb is that you should always try to use the exec format of the entry point instruction. That said, sometimes you need to run your command in a shell. Maybe you're in a situation where you have an environment variable that needs to be expanded. Or maybe you have another reason. The point is that you're now back to square one. Well, we would be if it weren't for the Linux exec command. As you can see, we're using the shell form of the entry point instruction. However, we've inserted the exec command in before the call to the script. The Linux exec command replaces the shell process with the script process. In other words, the process with PID1 is no longer the shell. It's the signal trap.sh script. Problem solved. Back in solution 1, I showed you that you can fix the my container doesn't stop right away problem. Just use the exec form of the entry point instruction and make sure that your program catches sigterm and then exits. But there is another way, one that doesn't require you to write signal handling code. All you've got to do is run a Linux init system on your container, and all of these problems will be gone. Let me explain. In a normal Linux OS, PID1, the first process, is the init system. It does two important things. First, it cleans up after dead child processes. Second, it forwards signals that it receives onto its child processes. Here's the problem. Ultra-minimalist Docker images, like Alpine and BusyBox, have been stripped of their init system. So, when you use the shell form of the entry point instruction, the shell is PID1, and your app is a child of PID1. But the shell won't forward sigterm onto its children. Thus, your app won't terminate gracefully, and then neither will the container. When you use the exec form of the entry point instruction, your app runs as PID1. While it will receive sigterm when you Docker stop the container, PID1 is special and therefore won't perform the default action and terminate. That's why we needed to trap and handle sigterm in our program. The simple solution to these problems is to run a lightweight init system as PID1, then run your application as a child process of the init system. There are three ways to do this. The first way is to add the init flag to the Docker run command. This tells Docker to use the built-in lightweight init process called tiny. The second solution involves running an init system as the default process of your container. For example, here is a modified version of the factorial images Dockerfile. Only two things have changed. First, the Dockerfile installs the tiny init system to the image. Second, it runs tiny as the default process. Python 3 and factorial.py are passed as arguments to tiny. When the container starts up, tiny runs factorial.py as a child process. Tiny then passes along any signals that it receives to its children. Problem solved. Keep in mind that different operating systems will require different methods to install Tiny. I recommend that you visit the Tiny Init System GitHub page if you intend to use Tiny with a parent image other than Alpine Linux. Your third alternative is to use a publicly available image which already has Tiny installed on it. You can find those through the TinyInit Systems GitHub page. I personally prefer solution number 2. Install it yourself. The reasons are twofold. First, the init flag solution does not work on a Kubernetes cluster. This is because you don't use Docker commands when running your containers in a Kubernetes cluster. However, containers which already have Tiny installed can run on a Kubernetes cluster just fine. Second, you can install Tiny on just about any parent image. This is more flexible than being forced to use a particular parent image just because it has a Tiny pre-installed on it. We are finally done with the entry point instruction. I know that was a lot, but it had to be done. If it's any consolation, that was the most complicated thing in this whole course. Now we can move on to the command instruction. The primary purpose of the command instruction is to provide overridable default arguments for the program specified by the entry point instruction. Let me try and make this a little bit clearer by showing you an example. Here is a toy Dockerfile. Here's what happens when we create and run a container derived from the Dockerfile. As you can see, the echo command prints out E1, E2, C1, C2. The point is that C1 and C2 were passed as additional arguments to the echo command. Now look what happens when we pass the argument pizza to the container. The container prints out E1, E2, pizza. This proves that arguments passed to the container override the elements in the command array. It's perfectly legal to have a Dockerfile which has a command instruction but doesn't have an entry point instruction. With this kind of setup, command specifies the default executable for the image, as well as any default arguments. As you can see, command is kind of like entry point, but they are different. The difference is that the values defined by the command instruction are overridable, whereas the values defined by the entry point instruction are not. To demonstrate this, I'm going to create a new Docker image. Then I'm going to create a container from it. As expected, the container printed out the command instruction arguments. Why don't we run the container again, but this time pass it the command ls-l to run. See? The echo command is overridden by the ls command. Here are some other things you need to remember. The command instruction has two forms. This is more or less the same as the entry point instruction. When you use the command and entry point instructions together, they should both be in the exec form. Trust me, you'll save yourself a lot of headaches if you follow this rule. Every Dockerfile must either have a command instruction, an entry point instruction, or both. But no duplicates, i.e., you shouldn't have multiple command instructions or multiple entry point instructions. You can override the entry point instruction if you absolutely have to by tacking on the entry point flag to the run command. Basically, this option is there for you for debug purposes. That covers the command instruction. The ENV instruction is used to set an environment variable in the image. There are two different ways to set an environment variable. For example, the first format only allows you to set one environment variable, whereas the second one allows you to set multiple environment variables on the same line. Time for an example. Here's a completely pointless Dockerfile which defines three environment variables: debug, color, and size. Notice that color and size are declared on the same line, which means that you need to separate the environment variable and its value using an equal sign. The next three lines actually use these environment variables. Docker substitutes the variable with the value at image build time. Notice that there are two different ways to reference an environment variable. Here's what the output looks like. In Linux, you always run as some user. The default is often root, but you can change that for a container using the Dockerfile user instruction. The user instruction sets the username, or UID. It can also optionally set the group name or GID. The results of the user instruction apply to subsequent run, command, and entry point instructions. This means that a container created from the image will run the default application as the user and group set by the user instruction. There are situations where you may want to be able to build different custom images derived from a single Docker file. You can do this by passing custom build flags to the build command. The Dockerfile can then create custom images based off of the flags and their arguments. To do that, you use the ARG instruction. The ARG instruction declares a variable which users can pass values to like this. ARG variables can then be used in subsequent run instructions. Let me show you a little example to make this a bit clearer. Let's create a Docker file that produces images whose containers greet you on startup. Furthermore, let's design it so that each image that we build can be assigned a custom greeting. We start with a BusyBox image. Next, we declare the greeting argument. This will hold the greeting which will get supplied via command line at the image build time. If we don't specify the greeting argument, its default value is hi. Here's the greeting script. All it does is echo out our greeting and then start up the shell. I wrote it out as 3 echo statements whose output is concatenated and stuffed in the greeting.sh file. I only did this to make it clearer to you what the script does. That's the hope, at least. Okay, so the key thing to take note of is $greeting. The $sign tells Docker that this is a variable. Docker then replaces the variable with its value at image build time, not runtime. ARGs are like environment variables in that way. Next, we make the script executable. Finally, we set it as the default executable. We're done going over the Docker file. Now let's use this bad boy to create 2 custom images. The first image that we'll create will greet us in Japanese. See? Just for good measure, let's create a new image which greets us in Spanish. Anywho, that covers the ARG instruction. Thanks for watching. See you in the next lesson. Adios, amigos. Sayonara. All the label instruction really does is add metadata to your image. Honestly, I rarely use it. The expose instruction declares that a container listens on a specified port. This declaration is basically just a form of documentation. It doesn't actually do anything. / is the default escape character in Dockerfiles. Use it to escape special characters. The / also escapes new lines, making it the line continuation character. Take a look at this Dockerfile for this newly supported Windows container. That / following C:, is a Windows path separator. However, Docker thinks it's an escape character, and therefore that the second and third lines are actually one logical line. This could cause Docker to choke. What we need to do is change the value of the escape character. The way you do that is with the escape parser directive. Here's the fixed Docker file. Now, the backtick is the escape character. I guess I gotta teach you about parser directives now. Parser directives are an optional, special type of comment. They have the format # directive equals value. Also note that they must be at the very top of a Docker file. There are really only 3 things you need to keep in mind with parser directives. First, you don't have to worry about parser directives making your images too large. They don't add any layers. Second, by convention, parser directives are lowercase. It's also the convention to add a blank line after the last directive. Lastly, you can only use a parser directive once. Ever. Or maybe it was just once in a particular Docker file. I don't know. Go with your gut. You want your images to be small and with few layers, so that they're fast to push and pull. Each image layer corresponds to a Dockerfile instruction. However, As of Docker 1.10, only the add, copy, and run instructions actually add layers to an image. Roughly speaking, the fewer of these instructions, the better. But remember that you need to balance the readability and maintainability of your Docker file against the resulting image size. So, we're going to talk about a technique for reducing the number of layers in the images that you build. We're going to talk about multi-stage Dockerfiles. Essentially, a multi-stage Dockerfile is split up into multiple independent stages. This allows you to copy just the files that you need from the previous stage into the current stage, leaving behind a bunch of files and layers which are no longer needed. This saves space and reduces the number of layers in the final image. Let's look at an example of a really simple Java program based off of the interview question FizzBuzz. The purpose of the program is to print out all numbers from 1 to 20, but for multiples of 3, print out fizz instead of a number. For multiples of 5, print out buzz instead of a number, and for multiples of both, print out FizzBuzz. For starters, take a look at a non-multi-stage Docker file. It compiles the Java file and makes FizzBuzz the default application. First, I'm going to build the image. Then I'm going to run it. The image is pretty large because the parent image is large. It's got useful things like the Java compiler to compile our code. It's also got the Java runtime to run our code. However, we could shrink down the size of our final image quite a bit. The final image does not need the Java compiler, nor does it need our Java source code, which is only needed to create the class files. All the image needs is the Java runtime and the class files created from compiling our code. So let's look at a multi-stage Docker file for FizzBuzz. This Docker file has 2 stages. Each from instruction always starts a new build stage. In this case, the first stage compiles the Java program. To do that, it needs the fairly large OpenJDK parent image. The second stage uses a much more slimmed down parent image. It has the Java runtime, but does not have the Java compiler. The copy instruction uses the from flag to copy all of the Java class files created in the first stage image into a new layer on the second stage. We are going to rebuild the image and compare its size to the previous FizzBuzz image. The multi-stage FizzBuzz image is almost half the size of the regular FizzBuzz image. If you don't want to have to reference a Docker stage index number, you can name stages like this. Remember the ARG instruction? Well, variables declared by the ARG instruction are only in scope in the build stage in which they're declared. You can extend their scope to the next build stage by redeclaring their variable like this. That's it. Now you know how to create multi-stage Docker files. Okay, before we close out this chapter, I need to show you how to push images up to the Docker Hub. To do that, you need an account. If you haven't already done so, go to Docker Hub and create one now. Before you can push an image up to Docker Hub, you need to log in. All that entails is running the docker login command and supplying the username and password to the image registry, Docker Hub in this case. The purpose of the push command is to upload an image to an image registry. The target could be a private or public registry. What I'm going to show you now is how to push an image up to a public repo on Docker Hub. The key lies in how you name the image. You see, the image name must have the format username/repo name. Let me demonstrate. Previously, we built the clock image like this. The name of the image is clock and the tag is 1.1. Now watch what happens when I try and push the image up to Docker Hub. We cannot push this up to the hub because the image name does not start with a hub username followed by a slash. So I'm going to rebuild the image, but this time include my hub username. Now we're going to push the image up to the hub again. Success! One last thing. You might be wondering why some images on Docker Hub don't have a username and a slash in the repo name. For instance, take a look at the Alpine image. It's just Alpine, not jsmith/alpine. What's up with that? Well, images that don't start with a username are official images. They usually correspond to big name technologies like various Linux distros, such as Ubuntu and Alpine, and big name DBs like Redis and MySQL. I always try to rely on official images for reasons of safety and reliability. All other images are uploaded by regular users and are not reviewed by Docker Inc.
At this point, you've learned how to create Dockerfiles, how to create images from Dockerfiles, and how to create and run containers from images. In the next chapter, we're going to briefly discuss things like volumes, container networking, and container orchestration, and how these topics relate to Kubernetes. Thanks for watching. See you in the next video.